The world is in the middle of its first, truly global energy crisis. Demand for energy is growing across many countries in the world. As populations increase, global energy consumption patterns reveal that the world remains highly dependent on fossil fuels. Harmful impact, limited sources, air pollution and price fluctuations of non-renewable energy sources leads to increase of global interest towards renewable energy sources. Wind is the second largest renewable source. In Sri Lanka, windy land represents about 6% of the total land area. The problem is, turbine operation and maintenance cost is high. Wind is unpredictable. Global statistics shows that turbine failures are frequent and increases maintenance cost. Solution: we introduce a power forecasting system and condition monitoring system for wind turbines. Our system is data-driven. SCADA data is given as input to the system. After pre-processing, required datasets power forecasting and condition monitoring subsystem, forecasted active power, and the turbine health, visualized in the dashboard, in real time. In this project we make predictions for two horizons, which are short-term and medium-term. Our primary dataset is from Manor Wind Farm. It includes following features. For further analysis we use two datasets downloaded from Kaggle and the dataset from Belgium Transmission System. We use historical output power as input feature. In pre-processing part, we handle missing data by adding average values, and there were no null values. Since basic machine learning models can't use to predict future values, time series forecasting models are used. ARIMA is the basic time series model, and we use ARIMA, which included integrated moving averages. Next was SARIMA, which takes seasonality of data into consideration. Those are already existing models. They were working fine, but we couldn't achieve a higher accuracy. Deep learning models. LSTM and GRU are advanced RNN models which are used to predict future values. Our 1D dilated convolutions model is a type of convolution that inflate the kernel by inserting holes between the kernel elements. All deep learning models showed excellent results. For medium term, a 2D CNN model was presented in ICCDS 2017. While enhancing the accuracy of this model, we implemented a much simpler 1D dilated CNN model. MSE was slightly better in our model. Supervised learning models require a labeled dataset to annotate data as normal and anomaly. We used clustering techniques. Using these, we could identify and annotate power curve underperformance failures and gearbox failures. Since the real-world datasets are unbalanced and not annotated, we proceeded with normal behavior modeling approach. In NBM, target variable, which is sensor data from wind turbine, is predicted using machine learning model. Deviation of predicted value from measured actual sensor data is considered as health index. Turbine failures are identified before the catastrophic stage by health index. We selected 4 input variables and predict the gear oil temperature using convolutional neural network. Health index goes beyond the threshold for the turbines with gearbox failures. Here is our dashboard internal architecture. Deep learning models running in the server generate the results from SCADA data and saved in MySQL database. Data fetched through API for visualization in WindBlaze dashboard. As additional option, Grafana dashboard developed for analytic purposes. This is a demonstration of our WindBlaze dashboard working.